Okay, this is part 2 of the January 2021 International A-Level Physics Unit 5 paper. I went through the first part, questions 1 to 12, in an earlier video, which you can find in the same playlist along with other exam papers from 2021 and 2022. You'll also find in the playlist, which will help you, some useful videos produced by other physicists which will help you with certain concepts and get you thinking beyond the syllabus, so it gives you a better depth of understanding. So in the playlist you'll find videos which are not produced by me. Have a look at them if you want to have a better understanding, especially the ones which show you how to do potential energy changes for objects in orbit, and why, for example, the potential is zero at infinity. The mathematics is done very well with the graphics that have been included, which I'm not able to do on my own device. Okay, so I would recommend watching those at some stage during your revision, especially if you're one of my students and you're confused about the difference between potential and potential energy for orbiting objects like satellites. Okay, so if you've watched the first video, that's great, thank you, and go back and watch it if you haven't done so, questions 1 to 12. Like each video you watch, because that's how YouTube works. I give you the model answers, and you need to show your appreciation. Each time you watch a video, give me a thumbs up, share it with anyone else you think will benefit, and help spread the word for the channel. We're over 1,000 subscribers now. We started over 12 months ago, and it's growing quite well, especially the A-level part. So I'd be grateful if you could do anything you can to spread the word. Okay, so question 13, it's is about, well, it starts with units, SI units. So let's have a look and see what we need to do. The SI system of units stands for Système International. It was established in 1960. So SI is in Paris, headquartered in Paris. This is why they, instead of saying International System of Units, they say Système International. And there are 7 base units in the system, okay? Including the meter, which is the base unit for length. So you already know this if you've done the introduction to physics. And then it says they want you to give the SI base units for energy. Okay, so you've got to explain where energy comes from. Well, work done is energy used. That's meant to say WD, not WB like it appears. And work done is force times distance moved in the direction of the force. And force, this is how I just did it. So work done is in joules. So units of energy are in joules. So joules and work are related. Okay, so force is mass times acceleration. So MAD, MAD, is equal to force times distance. And M is kilograms, and from here you can do it just from first principle. Acceleration, you know, is meters per second squared, and distance is meters. You then simplify it, and you get kilograms, meters squared, seconds to the minus 2. And that's how you do the first mark. Okay, a good revision of derived units. So joule is basically, 1 joule is 1 kilogram times meters squared divided by seconds squared. Okay, the next part. In the 17th century, I don't know how you say his name, Huygens suggested that the unit of length should be defined by the length of a second's pendulum. Okay, this is a simple pendulum that takes exactly 1 second to swing from one extreme to the other. Okay, that's half a period. And remember, the period is T equals 2 pi root L over G. And this equation is given to you in the equations at the back. Calculate the length of a simple pendulum that swings from one extreme position to the other in 1 second. Well, from one extreme position to the other, if you got a pendulum, from one extreme would be here, to the other extreme would be there, that time is half a period. So when it goes back again, that would be the full period. Okay, so T over 2 and T over 2. So T over 2, yeah, so would be 1 second, yeah? So T over 2 would be 1 second, so that's what they're trying to see that you can work out for yourself. So T would be 2 seconds exactly, yeah? And then you can just expand this equation, change it by squaring it. T squared equals 4 pi squared L over G, and then you want to make L the subject of the equation. Follow my algebra, put the numbers in. 2 squared at the top, and 4 pi squared is obviously 4 pi squared. Multiply 9.81 to 3 significant figures, it gives you 0.994 meters, or 99.4 centimeters. You could round it up to 2 significant figures because the data isn't given that accurately, 2.00. You could go 2 or 3, so either of these will give you a mark. Okay. It then goes on to say, suggest a disadvantage of basing the meter on the seconds pendulum. Well, this means that G would be constant wherever you go, but in fact G varies. Yeah, G is not constant everywhere on the surface of the Earth, so it wouldn't be a very good definition. You can see the mark scheme for other accepted answers, and then we can discuss them. Okay, let's see where the mark scheme comes up. So this is the 4-mark question, the third of the section B questions. Here it is. So we went through the answers already. Yeah. 2 significant figures is what they're quoting it to. G varies depending on the location on Earth. Yeah. Or you could put the meter would depend upon an accurate measurement of time. So that brings its own uncertainty in. Or the meter would depend upon the definition of the second. So right now, the meter is, the original meter was in before the modern definition, which is to do with the speed of light. The original one was actually a stick, which was exactly 1 meter long, and all other meter rules were correct according to the original one in Paris, which was kept in Sèvres near Paris. Okay, so question 15 comes next, and you can see that it's going to use PV equals NKT. If you're doing biology, if you're doing chemistry, they use PV equals nRT, which is the molar gas constant, whereas here we use K, which is the Boltzmann constant, and K gives this value, and you're given this value in your data sheet at the back. Looks like the first bit is just a quick use of the equation to work out pressure when you know everything else. So it should be quite straightforward. And then the second bit we'll have a look at, 14b. It looks like it's a little bit more complicated. You've got to work out the percentage remaining, yeah, which they say is 91%. So we looked at the answer first only because of the way the mark scheme is, I've kind of interwoven it with the exam questions. So it's easier when I'm running through it to find what I'm looking for and to explain things to you. Okay, question 15 will then follow. It looks like it's to do with logs and it's to do with radiation. Yeah. So it's like we got to look for the half thickness value of the absorber. Okay, so they're absorbing the radiation. Okay. So it's a logarithmic expression. There you go, and they found the thickness that would get the radiation down to 50% of the radiation without the absorber at all. Okay, so that's what the question 15 is about. So we'll have a look at both of those. So here's question 14. Xenon gas is used as an anesthetic. The gas is stored in cylinders, under pressure obviously. A cylinder with a volume of 6.0 times 10 to the minus 2 meters cubed, containing 7.5 times 10 to the 24 atoms of xenon. So that's your N. There's your V. The gas in the cylinder is at a temperature of 20 degrees centigrade. Now remember, in these gas laws, you've got to change it to Kelvin. So that'll be 293 Kelvin. You probably get a mark just for doing that. Okay. Then calculate the pressure. So you want to find P, use the equation that we just saw on the mark scheme, PV equals NKT. We know N, we know K is in the data sheet, we know temperature, and we know volume. So it's basically just algebra. Make P the subject of the equation, and then put the numbers in, and you get the answer to 3 significant figures as 5.05 times 10 to the 5 pascals, which to 2 significant figures would be 5.1 times 10 to the 5 pascals. I think 2 is the correct number of significant figures. All data provided was to 2 significant figures. Now, the next part of the question, they say gas is removed from the cylinder. Yeah, so that means there's less N goes down. The temperature of the gas decreased by 5 degrees centigrade. The temperature, therefore, is now 288 Kelvin. Okay, and the new pressure is 4.5 times 10 to the 5 pascals. I put as P dash, the new pressure. So the N dash, the new number of molecules, so the gas molecules, yeah? But they don't want the new number, they want the percentage of the original number that we have now. Yeah, in other words, what percentage have we lost, and therefore what percentage remains. So the answer is 91%. How do you get it? So we know N dash will be, using the same equation, it will be algebraically PV over KT with the new figures put in. So this figure will go in there. And where's the other one? T dash, the V doesn't change, K doesn't change. T dash 288 goes in there. Yeah, so the 288 is used. There it is. And the other 2 values don't change, so you can work out the new number of xenon atoms, and you just divide one by the other. Yeah, you can get rid of the power of 10 to 24 because both of them have the same power, and it's just a fraction, which comes out to 90.5% to 3 significant figures, and you should round it up, yeah, to 2 significant figures. The data provided is normally to 2 significant figures. So that's 5 marks done. 5 marks has been done. Okay. Question 15, I said it's about the radiation absorption. So let's have a look. A student investigated the absorption of gamma radiation by iron. Normally they do with lead. This is a core practical. Yes. So this is a core practical that you need to be aware of. You'd have to look, see which number it is. I can't remember. So the core practical is using this experiment, and you've got to use the half thickness, but they don't use iron, they use lead. Okay? So she placed a gamma source, yeah, there's your gamma source, in a holder to make sure it's directly in front of the Geiger tube, yes, to make it a valid experiment. So a short distance away, yeah. She then placed thin sheets of iron between the source and the Geiger tube, as shown. So there's the iron sheet in the middle, yeah. And the Geiger tube obviously is this object. The student then used 5 different thicknesses of iron and determined the count rate each time for each thickness. So the count rate would be R, okay, in this equation. The count rate with no iron sheet is R0 in this equation. So R equals R0 e to the minus mu x, which is a logarithmic expression, where x is the thickness of the iron, yeah, and mu is a constant. Yeah, there you go, mu is a constant. Alright, so it's very similar to other logarithmic equations you've used in other topics in year 13. After passing through an iron sheet, yeah, one of them, of thickness x, the count rate is given by the expression I just went through. Yeah, so then you can take logs, natural logs, and you come up with an equation which, if you put natural log of r on the y-axis, and you put x, the thickness, on the x-axis, then you can see that the use blue. The gradient will be mu. Let's get rid of that. I didn't mean blue highlighter. I meant blue pen. Okay, so the mu would be the gradient. Yeah, and it will be negative. The gradient will be negative. And the intercept will be the natural logarithm of the radiation that they measure without the absorber. Okay, that's here. Okay, and you can see that I've already read it as 6.85 on their graph, or at least that's what I estimate it to be. Okay, so the student used her data to plot a graph. The data is plotted. You can see I've done lots of calculations already. I've worked out the change in the y, yeah, and I've worked out the change in the x using as large a triangle as possible. So I've gone all the way down to the end of the graph, and there is the value there, and there is the value at the beginning. So basically goes from there to there, and that's what I've done here, okay, in the delta y expression. So I can see that it's gone down by 1.65, so that's why it's negative, and the x-axis is gone from 3.5 all the way down to 0. Okay? So this allows you to work out what mu is, because the gradient is delta y over delta x, and mu is a negative of the gradient. So that's what they want you to do eventually. So I've done it on the graph. I think that's always easier if you show all your figures on the graph. So I've kind of just talked you through this without looking at the question. So then you can see why mu comes to 0.471 per centimeter. Okay? So if you look at the question now, so you get the marks, 2 marks for doing this calculation, it looks like, and 1 mark for doing taking natural logs to show that it's in the y equals mx plus c format. Okay, going back to the question then, which we've already answered largely. It says, the student used the gradient of the graph to determine the value for mu, as I've shown you, and use this to estimate the half value thickness for the iron. We haven't done this yet. Okay, that's below. This is the thickness of iron that would reduce the count rate to half of the original without R0, basically half of R0. The radiation would go down to half of that value. What thickness would you need for that to happen? The student used a source that emitted gamma rays of a certain energy. Okay? So deduce whether the data the student obtained confirms this value. In other words, will the value of R, x half, will it give you the half value thickness coming to about 1.5 centimeters? So will we find that x to the power of half, or x half value thickness would be 1.5 centimeters. So we're looking, in other words, is to show that the x value will be 1.5. Okay, that's what we're looking for. We want to prove that the data given gives us x, will it give us x half to be 1.5 centimeters? Okay, so when r equals half, this is what I've said, when r equals half of the original, yes, let's do it this way, then the natural logarithm of the ratio will be equal to taking logs again, yes, from the original, r equals r0, so it's r equals r0 e to the minus mu x. When you take natural logs, you could put r underneath here, and it just saves you doing 2 lots of logs. So this will be r over r0 will be half. Yes, the ratio would be half, and then you can also change that to natural log of 2, yes? So that can change to the natural log of 2, which if you reverse it, then you get rid of the minus sign. Okay, that's basically, if you look at the logs, if you understand natural logs, you'll see that the minus sign will disappear. If you change this from a half to 2, yeah, it will give you 0.693 on this side. So just put it in a calculator and see that you understand how to do the logs. 0.471 was from our gradient, mu, yeah, and x to the half is the only unknown. So when you make x to the half the subject, you'll get a ratio which comes to 1.47 centimeters. Okay, because we're doing, this is per centimeter. Mu was per centimeter. We don't have to change the units, which is approximately 1.5 centimeters, which is close enough to the value given for the 1.1 mega electron volt gamma rays. So the 1.1 mega electron volt gamma rays is just a value given to them, and you don't have to do anything with it. It's just that's their energy. And obviously if they had higher energy, they'd be more penetrating. Okay? One would assume. And there we have another 6 marks done from this paper. Okay, question 16. Question 16, it's about a galaxy. In the 18th century, Herschel discovered an irregularly shaped galaxy. I have just corrected their English here. And I don't think that's irregular shaped is the correct English. You need an adverb, which would be irregularly shaped galaxy. This galaxy, now known as NGC 6052, is shown in the photograph. Okay? Just looks like a blob. Light from this galaxy has a redshift equal to Z value, yeah, of 0.0158. Okay? So you need to see the equations in the back of the sheet. Explain what is meant by redshift. Okay? So a redshift is the increase, it could be fractional increase in your perceived wavelength. So the original wavelength, and then there'll be a shift in the perception of the wavelength for the observer. So there'll be perceived wavelength difference by the observer, and that's due to the relative motion of the light source away from the observer. Okay? Its redshift means that it's moving away from. Okay? So, but it's due to the relative shift. So those are the two marking points that you need to put in to explain what redshift is. So a lot of this requires that you've done the donkey work, as I call it, with my students. Yeah? Ali, Taline. Ali is not so good at making his notes, but he's good at doing the exam questions. Now, you need to know all this when you're doing exam questions. Taline is good at making notes, but then doesn't do enough exam questions. So, guys, you need to make sure you're using this holiday period to get ready. You'll have a mock next week. So, it says calculate the distance of the galaxy from Earth. They've given you h0. Now, Taline, this was your talk. h0, wasn't it? So this is the value of Hubble's constant. And you know from this that the velocity is equal to h0d. And you can work out the velocity using the z value that they gave us above, because the velocity of the galaxy divided by the speed of light, yeah, in a vacuum, gives you the z value also. So you can work out the velocity because we know c, and we know z is given to us from above. Okay, z was 0.0158 in the question, and the speed of light is, to three significant figures, 3.00. So you can give your velocity to three significant figures. Okay, it's 4.74 times 10 to the 6 meters per second. So now we know v, yeah? You have v, and we know h. So the only thing you don't know is d. So make d the subject. Put in the value of h. Put in the value of v. Divide one by the other. Divide one by the other. And you'll get 2.93 times 10 to the 24 meters Well, what does that mean? It doesn't mean anything to me. So I worked it out. I used the computer to change it to light years for me because the mark scheme doesn't give it to you in light years. So it's nearly 0.3 billion light years. 0.3 billion light years. Now remember, the universe's age is 13 billion light years, or 13 to 14, 13.8 billion light years. A billion years. So that means it's been traveling for that much time to get to us. Okay, so I just thought it might be easier to change it from meters or standard form to that. Here's the mark scheme. So redshift, we talked about that. There's the answers they're accepting. There's the use of this equation. And there's the use of this equation, so it's really good revision. And then 16b we haven't done yet, so it looks like it's using the force between galaxies. Yeah, the inverse square law, so we're using F equals gmm over r squared, and the fact that it's 1 over r squared is what they want you to do, and then they ask you a question about that. Okay, so 16b, and then we go to 17 is using the same equation. Okay, let's see what we can do in this video. So here's 17, there's different ways of solving it. It says, I wonder how I did it. Okay, there's an example of the calculation. Okay, oh yes, I remember this. It sees 16 sunrises per day. That means it's orbiting whatever it's orbiting 16 times in a day. So here's part B. Recent photographs from the Hubble Space Telescope show that the galaxy that we're talking about, Herschel's galaxy, consists of two galaxies that are actually colliding. Yeah? So this is a more modern picture. You can see it's a more detailed picture. And they keep on improving telescopes. Now they've got the James Webb telescope. Hubble telescope is old now. The galaxies are accelerating towards each other. Well, why is that? Because they've collided. So they were accelerating towards each other, and they possibly still are. Explain why the acceleration increases as time passes. Well, as time passes, if they're accelerating towards each other, r diminishes. If r diminishes, yeah, so if r goes down, that means F must go up, because we are assuming the masses don't disappear and G is a constant. It's an inverse square law. So you've got to get the two marks here. So you're talking about the inverse square law. So that's one thing you need to mention. You need to say as they get closer, F increases, and therefore the acceleration will increase. Okay? And you can look at the mark scheme because I showed you already. You can go back to the video and stop the video when you want to have a look. Question 17. We'll do this because it's on the same theme. This is time, I'm doing the wrong thing again. Salyut 1 was the first Earth orbiting space station. It was built by the Soviet Union, launched into low Earth orbit 50 years ago. Okay? And that's what I was saying in the playlist. There are some other videos where they explain about orbits and objects in orbit. So really go and watch this. I think he's an American teacher. He's done lots of different videos, really short, brief, and he's done all the maths to show you how the potential energy changes, for example. Yeah? Now this is one of the videos will cover this content, but it's definitely worth using these videos to help you revise rather than from a book. Use these videos as well. So Salyut 1 orbited an average height above the Earth of 211 kilometers. Remember, that's above the Earth's surface. So you've also got to take into consideration that is 6.37 million meters away from the center of the Earth. So you've got to add the two distances together. So that will probably just get you 1 mark for doing that. I'm not sure. They then given you the mass of the satellite and the mass of Earth. Okay, and the textbook claims that the astronauts that are in there would see, yeah, a sunrise 16 times a day? Well, that depends on the period of their rotation, yeah? So their period of rotation should be 24 hours divided by 16. So 16 times faster than 24 hours. So we got to assess the validity of this claim. In other words, we got to show that the period of rotation for this satellite is going to be a 16th of 24 hours. Yeah. Now, one day, 24 hours is this many seconds, so they're helping you by giving you the SI units. So we're assuming, of course, that the orbit is circular. Yeah. Because otherwise you can't use the inverse square, you can't use the F equals gmm over r squared. So this is the equation that we've looked at before. That must equal its centripetal force, so it must be m omega squared r. Yeah, the reason I'm using omega squared, because you can then from when you work out omega. So we know, what do we know in this case? We know that these two force equations can be equated. The masses cancel, as I've shown. This mass cancel this. You don't even need the mass of the satellite. The r's we know. We know the r. There's r. Okay. And we know g. And we know m. So all you've got to do is put in r into that value there, and you get omega squared. So then you can square root it. Yeah. So if you want to get omega, you've got to square root all of that. So it's just number crunching. And once you do that, you'll get to 3 decimal places, 4 significant figures, 1.183 times 10 to the minus 3 radians per second. So sometimes it's useful to keep the more accurate value, because you're going to now use this value for omega to put it into this equation to work out the period that this would indicate. Yeah, knowing circular motion, you just divide 2 pi by omega, and you'll get the orbital period is 5,311 seconds. Again, we've used 4 significant figures, and we know one day is this many seconds. So is this, compared to this, 16 times smaller? So if you divide the big one by the small one, you'll see how many orbits you can do in a day, and it gives you an answer of 16.3. So we've just proven they would see more than 16, just over 16 orbits, sunsets a day. Yeah, so they're correct, and the ticks show where you get the marks. So there we have it. Question 17. Is that question 17? Yeah, 17a. So we've done 17a. But we haven't done 17A2. And this is what I was telling you. The guy in the videos, he shows how you can use this understanding of potential. Yeah, it's always negative because it's always less than 0. We define potential of gravity to be 0 at infinity, because obviously this value will only be 0 when r goes to infinity. Then the value of the potential will be 0. So in other words, when you're in a gravitational field, the only way you can escape is if you get far away enough where the potential will be 0, or the force on you will be 0. Okay, but so this is called the change in energy gravitationally is the potential multiplied by the mass. Yeah, so this gravitational potential is per kilogram. But if you like, the satellite has more, it's more than 1 kilogram. If you then multiply this equation by the mass of the object in the orbiting object, when you multiply, you then get a change in potential energy gravitationally. Okay, and this is what the next question is about, and this is why I'm saying watch those videos. Yeah, he explains all of this maths really clearly. Yeah, and his graphics are good, so it'll be a good thing to do if you find this kind of question difficult. And these are common questions. And then he goes to 17 part B, and then we're going to stop the video. Okay. because I've had enough of physics today. I did a GCSE session for my students this morning, and this afternoon I'm doing this A-level video for you. Question 18 then is about simple harmonic motion, so we're not going to go into that now. Again, they're using 2 pi f, 2 pi over omega, same as that. So it's about simple harmonic motion. I'll just pause the video so you can come back and look at the mark scheme before I do the next video. So that's going to be in the next next part of this run through. Okay, so the last part of question 17 is this part 2. It says Salyut made 3,000 orbits before falling back to Earth. Okay, calculate the change in gravitational potential energy of the satellite as it fell back to Earth. So that means it goes from its orbit 211 kilometers above the surface to the surface of the Earth. Well, that's what we're assuming. So the change in potential energy, is always the final potential energy minus the initial potential energy. So first you could work out the potential, because the equation they give you in your exam is the potential, which is per unit mass. All you've got to do is then multiply by the mass of the satellite, and you will change it to the change in gravitational potential energy. Okay, so that's what the guy in the video explains really clearly. Okay, so the equation you get in your exam is this one, which is the change in the potential, which is per unit mass, which is per kilogram. And the satellite was, I don't know how many kilograms, you've got to look on the question before. So the final potential will be the potential on the surface of the Earth. Okay? So that's going to be more negative than the potential when it's in orbit. So initial potential is minus gm over r when it was 211 kilometers above it. So the change in potential is the final minus the initial. So you can put gm outside the brackets. Yeah? And then all that's left in the bottom is, if you get rid of the minus, you'll see that this is correct. 1 over r, because this becomes plus, minus becomes plus, so I put 1 over r first, and this stays negative, so I put it afterwards. Okay? Now when you do the numbers, you will see that you'll get a negative over here. Okay? Now you just got to do number crunching. This is not the part of physics I enjoy, doing all the number crunching, but you put the numbers in and you do it properly on your calculator, you should get 2.00 times 10 to the 6. That's the amount of joules per kilogram, and all you've got to do is multiply the change in potential by the mass of the satellite, which is 18,400 kilograms, and you'll get a change in potential energy, because it's not 1 kilogram. If it was 1 kilogram, it would be this. That's for 1 kg. Multiplied by 18,400, and you get the change in potential energy. So E grav, delta E grav, is the change in potential multiplied by the mass of the object that's orbiting. And it's now fallen that 211, and the change in potential energy again is negative because it's decreased, and remember the maximum is 0, so it's always negative. Okay? Let me just remove this circle so we can see the power is 3.7. I've done it from 3 significant figures to 2 significant figures, so here's 3 significant figures. My final answer is to 2 significant figures. Is that reasonable? Yes. You have to go back and look at the figures. I think 3 significant figures will be fine as well. Okay, now the final part of this question and this video is part B. Salyut burned up over the Pacific Ocean as it entered the Earth's atmosphere. So you've got to explain why it burned up. So this is not mathematical, this is qualitative. Well, it reaches a high velocity. And high velocity, as you know from year 12, F equals 6 pi r e to v, if it was spherical, you could work out exactly what the drag force was. So it's going to create a large drag force because it's moving so fast. You could probably work out how fast it's moving if you work out 2 pi r for its orbit, and you know the other data that we had before, so you could actually work out the velocity. And then the resistive forces are so high, that the work done by the frictional forces or the resistive forces creates heat, So they've actually got material on the thing that will, for example, when they had the space shuttles, they had material on the surface of the space shuttle that could absorb this amount of heat, had a very high heat capacity. And this kinetic energy is then slowed down and converted into thermal energy. So somehow you got to get 2 marks by explaining this, and you can go back and look at the mark scheme. Let me just end the video by showing you the final bit of the mark scheme. Okay? Then you can stop the video and have a look at it. So while I'm talking, so if you found that useful, don't forget, show your appreciation each time you watch a video. Like the video, share it with your friends, subscribe. Okay? As the guy in the video says, sharing is caring, and we need to get the more and more people using YouTube. As one of my students today said, GCSE student said, the YouTube is the most useful thing that she finds when she's revising, because basically you've got your teacher available to you at home. Okay, I hope I explained things clearly. I try to do it as clearly as possible. So hopefully catch you in the next part of this video. Bye for now.